Hey everybody, Mr. Judson here. So today we make what we did last time we met on Monday easy. We make derivatives really easy. Okay, we had this process we had to go through where we had to write all this stuff out. But really, if I say to you y equals 3x squared minus 4x plus 2, I should be able to just look at this and say the derivative of 6x minus 4. Let me do another one. This time y equals 5x to the 7th plus 3x to the 5th minus x. And I should be able to just look at that and say y prime is equal to 35x to the 6th plus 15x to the 4th minus 1. Can you imagine if we had to take this and do x plus delta x raised to the 7th power? X plus delta x, so on, 7 times, and multiply that out. That's a disaster. I bet every one of us would make a mistake doing that. But we have a shortcut that allows us to look at this and go straight to the derivative. And it's pretty easy. Some of you may have already spotted it. All you do is take the exponent times the coefficient, so 2 times 3 is 6, and subtract 1 from the exponent. I now have x to the 1 power. Think of this as minus 4x to the 1, so I multiply 1 times negative 4, there it is. Subtract 1 from the exponent, you get x to the 0 power, which anything to the 0 is 1. So really I just have a negative 4 times 1. What happened to the 2? Well, if you think of that as times 1, but I'm going to write it x to the 0 power, right? So 0 times 2, that's 0, times x to the whatever, I don't even care anymore, 0 times anything is 0. So the derivative of a constant, when I say constant I mean just a number, is always 0. So we didn't write anything down over here. Okay. Multiply the exponent times the coefficient, so 35. Subtract 1 from your exponent. Here I get 15. Subtract 1 from the exponent, I get 4. This is a negative 1 times x to the 1 power. So exponent times the coefficient, that's a negative 1. Subtract 1 from the exponent, you get x to the 0, which is 1. And so, yeah, the derivative of that is just negative 1. So what we need to do is we need to write down a couple of rules that we're going to follow. First rule is going to be for this right here. When I took the derivative of a constant, I got 0 and wrote nothing down. So we're going to write our rule this way. So remember I told you there's a lot of different notations for a derivative? d dx of something. That means take the derivative of what's inside of here with respect to the variable x. So a constant means just a number. And that's always going to equal 0. Okay, what's the derivative of 35? 0. What's the derivative of pi? That's just a number. 0. What's the derivative of the square root of 7? 0. Right? Derivative of 1/2? 0. That's what this is saying. So that's rule number 1. Rule number 2. The derivative of a constant times the variable x. So this just means my exponent is 1. And so that's kind of like what we saw right here with this term. Okay, it's a constant times x. And the derivative was just that constant. And it's because what we have is an exponent of 1, so I multiply that. When I subtract 1 from the exponent, I get x to the 0, which is 1. All right, so this is just going to equal whatever that constant is. So what's the derivative of 5x? 5. What's the derivative of x over 2? Well, that's the same thing as 1/2 times x, so the derivative is 1/2. Okay? And then our third rule, and really this rule really includes these two, and it's the one we're going to look at the most often. Okay? The derivative of a constant times x raised to the nth power. And what we're going to do is we're just going to take that exponent times the constant, so Cn times x raised, and then we're going to subtract 1 from the exponent to the n minus 1. Multiply the exponent times the constant, which we're doing here, subtract 1 from the exponent. These are our rules to follow. Okay? Now, this is really important to understand. What that means is, everything that I take the derivative of today, I have to be able to write it as a number times a variable raised to an exponent. Not a number divided by a variable raised to an exponent. That's a whole different problem. All right? I have to be able to write this as a number times a variable raised to an exponent. I don't care if that exponent is a fraction. I don't care if it's positive or negative, but it's got to be written this way. All right? So, using our shortcut now, this means finding a derivative is going to go really fast. So instead of doing just a few problems, we should be able to do a lot of problems, right? All right, number 1, f of x equals 3x to the 6th power minus 2x cubed plus x. Find the derivative. You guys should all be smiling right now, because if we were using our definition of a derivative, this would probably take us about 10 to 15 minutes. Because we've got to do x plus delta x, or x plus h, to the 6th power, and we also have to cube it. So it's going to take a while to get that information. But f prime of x equals 18x to the 5th minus 6x squared, constant times x, that's just 1. Trying to picture the guy who first discovered this rule. They're going through this big long process with, f of x plus h minus f of x all over h, and the limit as h goes to infinity. Although I think h came later, they were probably still using delta x. And I'm sure somebody, when they figured this out, they were like, oh my gosh! Because this is huge. I mean, this saves us a ton of time. So this is really a big deal, this shortcut. Right? Let's do another one. F of x equals x squared over 3 minus the square root of x plus pi. Now, you got to remember, I have to be able to write this as a number times a variable raised to an exponent. If I can't do that, I can't do this problem. So that's the first thing we got to think of. How do I write this as a number times a variable raised to an exponent? You guys try. Again, the shortcut's amazing, because if I had to plug in an x plus delta x, or x plus h, whichever one, and do the limit, this is going to take a while to get through. But if I rewrite this like this, 1/3 times x squared minus x raised to the 1/2 plus pi. Now, this is important too. Don't write f prime of x here. That's not the derivative, that's just the same function, right? I don't want to write this. Not until I start multiplying by the exponent and subtracting 1, which I'm going to do now. So now I can say f prime of x is equal to, if I multiply by 2, I get 2/3 x, subtract 1 from the exponent, it's now 1. Here when I multiply, I've got a negative 1 times a half. That'll be a negative 1/2 times x raised to the, if I subtract 1 from the exponent, 1/2 minus 1 is a negative 1/2. And this is just a constant, it's just a number. So the derivative of that is 0. I think we become better at working with fractions once we start doing the derivative like this, because we have to. It happens so often, we need to be able to subtract with fractions. So the only thing that's left here is, to be considered simplified, we don't want to have any negative exponents. So I do need to drop this back down below the fraction bar and make that exponent positive. I would probably write this like this: 2x over 3 minus 1 over 2, and then x to the 1/2 is the same as a square root of x. So I'd write that in there. I will always leave this as a fraction, except for the fraction 1/2. Okay, 1/2 we just know is a square root when it's in the exponent, and so I think we should keep that straight. You know, if this was 1/3, then it would be the third root, but now that gets harder because I got to write this little tiny 3 in there, so then I would probably leave it as a fractional exponent. If it's something like a negative 4/5, oh yeah, that's just going to stay at, you know, x to the 4/5 when I drop it below the fraction bar. Okay, but 1/2, I think we just want to remember that that means a square root. And so if you write it down, it helps you remember that. There's my answer for that one. Now, this is kind of cool. We can check this on our graphing calculator. Let me get back to the original function. And I'll pull up the calculator. So I want to do the derivative of this thing right here. And if you look right here where the 8 is, the second function option is a d. D for derivative. So if I go second d, that means the derivative of whatever's inside here. All right? So I'm going to punch in this expression. I've got x squared divided by 3 minus the square root. So minus root x. I'll punch in exactly the way I see it, plus pi. All right, and then our, when we go back to this, d over dx of whatever, that's equal to our d on the calculator. But the dx part, we still need to put in there. So the calculator wants to know the derivative with respect to what? So I need to go comma x. That's how the calculator takes the dx part. And we have to do that because you can actually do the derivative of an expression with x's and y's in it with respect to x. That's something we'll talk about later. But that's why we have to tell the calculator with respect to what. And so then close parenthesis, and I hit enter. There's my answer. 2x over 3 minus 1 over 2 root x. All right? So you guys should always be able to check this on the calculator, even if it's an even problem. Oh, no, that means we can't use our calculator on the test. Yeah, our next test is all about derivatives and shortcuts, so obviously we will not be able to use this, okay? All right, let's try another one. What if I have something like this? F of x equals 3.2 over x to the 4th power. And I want to find the derivative. I've got to be able to write it as a number times a variable raised to an exponent. Remember, I don't care if that exponent's positive, negative, decimal, fraction, whatever. It's just got to be written that way. That's all we know so far. You guys try it. Alright, so this equals 3.2 times x to the negative 4th. If I bring this back up, it just changes the exponent to the opposite. Right? Anytime you take an expression with a variable and an exponent, and you move to the other side of the fraction bar. I don't care if it's from numerator to denominator or denominator to numerator. It just changes the exponent to the opposite. Okay? So now I have a number times a variable raised to an exponent. So I can say f prime of x is equal to a negative 3.2 times 4, that would be 12.8, times x to the subtract 1 from the exponent. So a negative 4 minus 1, that would be a negative 5. Right? Not a negative 3. You've got to be careful there. And then that's it. So this equals 12.8 over x to the 5th. And there's my answer. All right, got one more problem to look at. What if I had something like this? This is number 4. F of x equals 3x squared minus 4x plus 5 all over x. And we look at that and we go, oh boy. I don't know how to do a derivative yet where we're dividing things. I don't know how to do that. We'll learn. We will learn. But I have to find a way to make this look like some of the previous problems. It's got to be written as a number times a variable raised to an exponent. It's got to be a series of terms. Okay? You guys see if you can figure out how to do that. All right. So here's what we need to do. I need to look at this and I need to think of this as the least common denominator and then separate this into 3 different fractions. So 3x squared over x minus 4x over x plus 5 over x. I got to do that first. I got to get each one as their own term, and then I can write this as a number times a variable raised to an exponent. So here, x cancels with an x, I get just 3x. Here the x's cancel, I get minus 4. And here, if I move that up, the exponent becomes negative. So I've got x to the negative 1. Now I'm ready to take the derivative. Now again, I can't even imagine what this would be like if I had to plug in an x plus delta x here, here, and here, and then somehow simplify that. Pretty sure I could get through it, but I wouldn't be very excited about it, right? This is like, this is easy. So here's my derivative. Derivative of that would be just 3. Derivative of a constant is 0. And here when I multiply, I get a negative 5x, subtract 1 from the exponent, I get a negative 5x to the negative 2. So all I really have to do now is just get rid of the negative exponent. And so what I've got is f prime of x equals 3 minus 5 over x squared. Done. God, I like shortcuts. Shortcuts are nice. I can't think of a better shortcut in math than this one right here. This saves us so much time. All right, so if I was to ask you guys to find all right, so I ran out of memory on the memory card, and so I got cut off somewhere here, so I had to come back and do it over again. But I think this is where we finished. Once we found the derivative, find the slope at x equals 2. It means I just have to plug a 2 into here and see what I get. So 2 squared would be 4, so 3 minus 5 fourths, that would equal 7 fourths. Right? That would be the slope at the point where x equals 2. All right, we've got one more question to try here. So here we want to find the equation of the tangent line for this function at the point where x equals 1. Okay, you guys go ahead and do that. All right, so the moment I see these words right here, equation of a line, in my head I'm thinking there's two things that I need to know. I need a slope, I need a point. Once I have those, this is an easy problem, okay? And it's really not even that hard to begin with, especially now that we've got a shortcut. So I'm going to find the point first. So if I do f of 1, that means I'm just plugging this x value back into here to see what I get for y. So that's going to be 2 minus 1 over 1, that's 1. So 1 comma 1. There's my point. And now I need a slope, which means I'm going to need the derivative, right? Because every time we see that word, slope or derivative, they mean the same thing. They're interchangeable. So my derivative, if I multiply here, I would get 4x to the 1 power. This right here is going to be a negative x to the negative 1. So if I multiply the exponent times the coefficient, negative times a negative, that's positive. And I would get x, subtract 1 from the exponent, that would be a negative 2. So there's my derivative, which really means 4x plus 1 over x squared. So now what's the derivative at 1? So f prime of 1 means I'm plugging 1 into the derivative. I get 4 plus 1 over 1, that's 5. There's my slope. Now I just got to write the equation of a line. So I've got y minus the y value equals the slope times x minus the x value. And so that means y minus 1 is equal to 5x minus 5. If I add 1 to the other side, I've got y equals 5x minus 4. And there's my tangent line. Now if I want to check this, I could check this pretty easily on the graphing calculator, right? If I go to the graphing calculator, so there's my original function, here's my tangent line. And so what I want to do is I just want to look at it and see if it looks like a tangent line at the point 1 comma 1. So if I go zoom option 4, all right, that's not really what I was expecting to see when I graph this. I don't know if maybe we have some kind of a slant asymptote here. I'm not really sure. I don't see enough of the picture to feel really good about this. So I'm going to change the window. And I'm really only interested in what's happening at x equals 1. So I'm going to go from 0 to 2. And for my y values, I'll go from, let's go negative 3, but I'm going to go a little higher. I'm going to go to 10. And we'll graph this and see what it looks like. All right, so right here's the point 1 comma 1, right? And the line did come by and sort of hit the graph there, but is it really a tangent line? And so, you know, one of the questions that often comes up is, if I have a curve like this, what does the tangent line look like at that point of inflection? It's where the curvature changes, right? And if I draw my tangent line, it looks something like that. And we look at that and we go, that doesn't quite seem right. You know, if I think of a circle, tangent line comes by and nicks the edge, it doesn't go through the circle, right? This is not a tangent line. I'm only intersecting the circle once, but it's not a tangent line. So why is that a tangent line? Well, here's why. Let me get rid of this. Let me go back and undo this picture. And I'm going to draw it slightly different. let's just say I only draw this picture of the curve, and I want to know what does the tangent line look like at a point that's really close to the end of that curve. Maybe not quite, there's a little bit of blue space after it. Well, the tangent line would look something like that. And it should go this way as well, but I'm not going to draw that on purpose. What if I had a curve that looked like this, and I want to know what the tangent line looks like pretty close to that end point? Really close. Okay? The limit as that point gets closer. And so I draw a tangent line like this. Well, now, what if those two things were connected? These are both tangent lines, right? Think of like x to the third power. What does that look like? So if I take this whole thing here and I slide it up, I lost my point, but that's okay. Come on. Something like that, it looks like that tangent line is going through that point of inflection. All right, so we can kind of see it. It's sort of like if I have a piecewise function, and this has an open circle, and this one has a solid dot, and the solid dot fills in the circle, it's now continuous. Same idea here. This was a tangent line to the curve here. That's a tangent line to the curve here. So why isn't that a tangent line to the entire curve? Right? So we will see tangent lines intersect through the curve. Let me just show you like one more example. So here's a curve, and I want the tangent line right here. Well, that makes sense to us. You know, it looks like it just went by and nicked the edge of the curve, but what about this over here? It's hitting the graph again. Well, forget about that. Relative to this area right here, does this line segment come by and just nick the edge of the curve once? Yeah, it does. But it does in reality intersect somewhere else. That's kind of what happens at a point of inflection as well. All right. That's what we have for today. Let me get you guys a homework assignment. All right, here we go. We've got we're still on assignment number 7. This is Wednesday's portion. We're on page 118, and we're going to do 11, 13, 17, 21, 27, 35, 43, 45, 55, and 59. I think you guys will like this assignment. I think it's going to go a lot faster than the last one. Shortcuts are a good thing, and you know, derivatives just became easier. So, yeah. All right, that's it. That's all we have for today. I will see you guys on Thursday. All right, take care. Be safe.